Okay, so hi everyone, I'm Akim Tsvigun, and I'm gonna teach classes in machine learning 2 together with my colleagues Leonid Sanashkin and Artem Vazhentsev. So as for the groups, it will look as follows. First of all, let's speak about the topics of the course, because in my opinion, the name of the course is slightly vague. So probably some of you know that there is a course on the program applied math and informatics, which is named the same, machine learning 2. But frankly speaking, our program will be completely different from the one which is there. So on that very course, they learn some advanced concepts of machine learning, some kernel methods, etc. And our course will be mostly devoted to deep learning and NLP. So as probably some of you know, NLP is natural language processing. That's the area of deep learning which is devoted to working with textual data. So about the topics of the course, by the way, I can turn on the camera if that's okay. So the plan of our course. Module 1 will be fully devoted to introductions to the deep learning. So to my knowledge, you still didn't have any course devoted to deep learning totally. So the first module will try to get acquainted with all the areas of deep learning. We'll get acquainted with natural language processing, with computer vision, with speech recognition, and so on. And certainly we'll learn as much as possible about neural networks, how to train them, how to apply them, how to test their profitability, and so on. The second and the third module will be devoted to natural language processing. And here I have some very important idea to convey. So I understand that you are all from the 4th year of education, right? And well, the majority of you already work, and some of you work in some other areas like computer vision, probably working with tabular data. And those guys who want to tie up their career with some other areas, probably they do not need natural language processing in such great amount. So my idea is as follows. The first module, it will be really crucial, it will be vital for, I guess, probably each of you, because we will embrace all the base concepts of deep learning on some other areas. You can feel them, you can try them, and select probably the most interesting and exciting for you. And as for the second and third module, they will be like a bit easier, because I understand that some of you, well, probably do not need natural language processing as a whole course, which will last 2 modules. So the first module you work, and the second and the third module, if you don't need it, if you are sure that you will never face natural language processing in your career, in your projects, then you can probably, well, not skip, but work a bit less. Okay, so the assessment formula, one of the main components of each course. So you'll have a score for each of the modules. You can see the formula here, and the final score will be computed as the arithmetic mean of these modules and the exam. So you'll have a midterm at the end of the first module devoted to Intro to Deep Learning program, and you will have an exam at the end of the course. Of course, we'll have some automatic, I don't know how to say it in English, automatic assessment, right? So for now, let's have it this way. If you have scores 7 or greater for each of the modules, you can get the automatic score for the exam computed as, again, the rounded arithmetic mean of your scores for each of the modules. If for some of the modules you have less than 7, then you, for now at least, probably cannot get the automatic point for the exam. Okay, so some important materials. All the materials, all the seminars, lectures, they will be provided on GitHub. The recordings of the lecture and the seminars will also be uploaded to YouTube to like official Faculty of Computer Science account. Yeah, the Telegram chat. I hope all of you have already joined it. If not, please do so. As for Wiki, I have not created it yet, but it will like I will do it very soon. And okay, so like some advertisement. I don't know, like all the teaching team, Leonid, Artem, and me, we're all colleagues in NLP group in AIRI, that's the Artificial Intelligence Research Institute. So probably some of you will get interested in that to have some internship because we have some well, great projects. Okay, so a bit more formal moments. As I've already said, all the lectures and the seminars, they will be translated to Zoom, but let's make one fair gentleman and ladies agreement. So I understand that some of you have some other priorities and you like will not devote much time to this course. Well, probably that's okay, but I really hate cheating because it makes these like guys with different characters in you probably know what I mean. So the agreement is as follows. For now, we agree to write all the tests and even the midterm, as for example, I don't know what will happen in 6 months, but nevertheless, we like allowed to write all of them online. But if at least once you are caught cheating during online, then you lose this opportunity till the end of the course. Well, I guess that's pretty fair. So if you do not cheat, okay, online is for you. If you cheat, well, probably you have to do this offline. Some instructions how to write these tests online. I guess on all your previous courses you already had them, that you need to show your face, your hands, show your screen. I will send it a bit later when we'll have our first test. Yeah, and probably the last but not the least point about our lectures. So my main purpose, my goal is to convey the material to each of you. But of course, for now, I know none of you. And of course, we'll get acquainted throughout the course, but I cannot live in your body. I cannot understand when the material is easy for you, when the material is extremely hard for you. So when you do not understand something, when you feel that I'm going a bit fast, then please stop me. It concerns both the ones of you who are here and the ones who are on Zoom. Please stop me and we will like repeat this material, I don't know, probably one or several times, because the main goal is just to make the material easy to understand for each of you. Please don't hesitate. Okay, so if any questions, happy to answer. Okay, if no questions, then let's try straight. Let's start straight away with our topic. By the way, another one question. Please raise your hands, the ones who do not understand Russian. None of you. And in Zoom, yeah, for those who are in Zoom, please write everything in chat. If there are like 2 or 3 minutes and I do not react, please feel free to enable your microphone and ask this with your voice. I guess this will be the on Zoom. Okay, so my idea was the one that when we speaking about some very hard concepts, I can sometimes use Russian, but if like there are students who do not understand completely, well, okay, we'll find the solution. Never mind. Okay, so let's start with our lecture. That's it. Okay, so the plan of our today class. First of all, we need to revise some general machine learning notions. I know that last year you had a course, Oleg, I do not remember the surname, Melnikov, he was the teacher, right? Okay, great. So the next point is the gradient descent. Again, you know this, but we need to revise this a bit because this is like the main idea of deep learning, the main idea of training the deep learning algorithms. The next will be overfitting and how to deal with it. The order is slightly mixed up. The next will be the neural networks. We'll build our first neural network. We'll see how like to explain all this mathematically. And if we have some time, we'll also speak about the gradient descent extensions. Again, probably on machine learning 1, you already spoke about these RMS prop, Adagrad, momentum, Adam methods, but we'll need to revise them since they are very crucial in deep learning. So let's first revise a bit the tasks, the types of tasks in machine learning. So we have the regression when the output is a number. We have the classification when we need to sort our object and assign one or several labels to it. We have the clusterization when we do not know the true labels. And we also have this dimensionality reduction when the data has a lot of features and we need to reduce them. And now probably will be the most interesting slide. So the which areas of machine learning and deep learning exist. So on machine learning 1, you embraced the following areas: tabular data analysis. Of course, the majority of machine learning algorithms like boosting, bagging models, and so on, they are devoted to tabular data analysis. You probably also embrace the unsupervised learning, these algorithms of clusterization, of dimensionality reduction. Okay, probably you had some courses or you will face some courses for time series analysis. Of course, this area of machine learning can be solved without deep learning, and on like many projects, indeed, they do not use deep learning, but using the deep learning algorithms, you can get like high quality in, I guess, about 90% of cases. And as for these 4, let's for now exclude the recommended systems like natural language processing, computer vision, speech recognition, and reinforcement learning. They simply cannot be solved with an appropriate quality without deep learning. So, like when we have an image and we have to classify it, of course, using a boosting or linear regression will not give us some decent quality for this. So there are some base algorithms, but to have some really good quality, we need to learn the deep learning. No, what's the purpose of this image? Okay, so let's quickly recall the main attributes of machine learning pipeline. So what do we have? We have our model, like the rule according to which we make the prediction. For instance, for linear regression, we need to multiply the features by the weights of our model, probably add the intercept if it exists. And here we are, there is the forward pass. For logistic regression, we also need to apply the sigmoid function at the end of this forward pass. We also have these model parameters like weights, predicates for trees, and so on. We have some hyperparameters for linear regression. There are no hyperparameters. Well, no, adding intercept or no. For like regularization models like cluster rich regression also have this regularization coefficient and so on. Loss function, which defines how to train our models. So again, for linear regression, we can use this analytical solution and the loss function as MSE, but also probably you spoke about quantile regression, which uses the mean absolute error as the loss. And of course, they'll have like different training procedures. The optimization algorithm, like either use an analytical solution or use some variants of gradient descent, like stochastic gradient descent, or again momentum, Adam, and so on. And we also have some quality metrics which are really important because the majority of models use this so-called early stopping algorithm, which breaks the training when we see that the quality on validation data does not increase, and we need to measure this quality very precisely. Like for real-world projects, this is probably some business metrics. For some research projects, these are the metrics which are stated to be used for these tasks, and so on. The model families. So basically, there are 4 model families. These are the linear models, the tree-based algorithms, the nearest neighbors methods, and the neural networks, which are completely different from the previous algorithm. Well, the most similar family of models to neural networks is probably the linear algorithms, but at the same time, the main attribute of neural networks is that they allow to make some non-linear transformations of data. Let's quickly recall the features type. We have this binary and numerical, which can be used straight away in our model. We have the categorical features, which are hard to be used for linear methods, like we need to apply this one for encoding, and they are easier to use for some boosting methods. And this, the most probably covered, right, feature ordinal, which is sometimes hard to be distincted from the numerical feature. For instance, such features as the number of months, which is conventionally like January 1, February 2, and so on. In most cases, this is the ordinal feature. And what does it mean? It means that we need to treat it as a categorical feature rather than a numerical, because it will provide a lot of more information in such a case. Okay, so let's now quickly recall the base machine learning concepts. So the supervised learning, the idea is very simple. We have some features, we have some target value, and we need to make the prediction which would be as close to the target value as possible. I don't think we'll need it. Yeah, by the way, I forgot to mention one important idea. As for the lectures PDFs, they will mostly be very long. For instance, this one consists on 130 slides, and their main purpose is not for you to only observe what happens there. It's like probably an additional supplementary material to the lectures, so that when you have some tests or midterms, you can quickly open them, slide them till the end, and recall some key ideas for you. So don't treat it as I read the lecture and that's okay, I grasp all the material. Okay, so the linear model, we remember how it makes the prediction, one straight line if we depict this in 2-dimensional space. The rule of how to apply this, the X is a matrix of features and observations, the W is the vector of our features, and we simply apply it by multiplying the transposed weights vector to our data. The last functions, how to measure the quality. We have this conventional mean squared error, which is used for linear regression. For classification model, can anyone tell me the loss function? That's great for multi-class classification and for binary. Okay, and another one. And how the name of the binary entropy, the conventional name? Okay, that's the log loss. And if we have the multi-label classification, so when we have one object and several classes can be inherited by these. For instance, when we have to classify the genres of a film, it can be both a comedy, a tragedy, a thriller, and so on. Which loss function we would use?
You mean multi-class?
That's multi-label. So, okay, I understand we need to revise this a bit. So, the binary classification easy. We have two classes. We need to use one of them. Multi-class classification. We have several classes, more than two, and each object strictly has only one label. And multi-label classification is it is like you face it much more rarely, but nevertheless it exists. Some object may have several labels assigned to them. So we know that for binary classification we use the log loss, for multi-class we use the cross entropy, and for multi-label classification.
Is the number of labels constant? Like should we?
No, it's not constant. So like one object can have only one label assigned, and like the second object can have 3 or 4 labels assigned. Okay, I see you have not touched upon this topic. We'll speak about this probably on the next class, but for now you can recall that for multi-label classification, we also use the binary cross entropy. That's the log loss. By the way, this was the question which I had on the interview in Google. So like they like to ask such type of questions. Okay, moving on. So the linear regression, the exact solution, it looks as follows. But the problem is that when the X matrix of observation and features is large enough, if there are a lot of features, if there are a lot of observations, the complexity of this operation will depend like cubically, right? So like in degree of 3 from the shape of it, and it is really hard for you can test it that when you have like 10,000 of observations, not a large data set, and you have about 1,000 features, the analytical solution will like last eternity. So the linear models can, of course, be trained analytically, and for logistic regression, can anyone please tell me the analytical solution for logistic? You have not spoken about the maximum likelihood method. Do you know what it is?
Yes, but it does not.
It has through the maximum likelihood. Okay, let's leave this for now. Okay, so the same about logistic regression. As for the loss, yeah, let's quickly recollect this. So that's the formula of the accuracy, but the accuracy cannot be applied as the loss function due to 2 major reasons. It's not differentiable, and it also does not incorporate the confidence of the model. So in a lot of applications of classification methods, we need to know the probability of the class, and the accuracy does not take this into account. So we need to use some losses which would do this. Like there are some extensions of squared loss, and by the way, an interesting point was discovered last year in one scientific paper that training a classification model with MSE loss can sometimes lead to state-of-the-art results. But let's leave it for now. So how to make the prediction for the classification task? We have some so-called logits, the class scores from a linear model, and we then apply the softmax for multi-class case. The softmax, do I have to remind this formula, or everyone remembers? Huh? Yeah, sure. Okay. So how to make it visible for you? Let's write it here. So what's the sigmoid which applies for binary classification? The sigmoid is 1 divided by 1 plus exponent in power of minus x. That's the sigmoid, and it's limited by the values 0 and 1. So when the x is going to minus infinity, we'll have the 0. When it goes to plus infinity, we'll have 1. And the softmax is just the generalization of sigmoid for multiclass case. So I do not remember whether there is like a special Greece symbol for it. Softmax looks as follows. We need to exponentiate each probability and divide by the sum of the exponents of all the logits. So it looks as follows. Softmax x will be as follows. Phi divided by the sum. The ones who are in Zoom, is it visible for you? Please write in the chat so I can see this. Okay, so the idea is as follows. We exponentiate each component, then divide by the sum, so that what are the benefits? The sum of the values is equal to 1, since we divide by their sum, and each value lies in the diapason from 0 to 1, and it is treated as the probability of the following class. So that's the softmax. Okay, let's move on. So the loss function, we have already spoken that the log loss and the cross entropy are used for this, but okay, I see that there are probably some gaps. Let's recall these two notions as well. So what's the cross entropy? It's easier to start with this for multi-class case. There is like nothing, I don't know, frightening in this. The cross entropy, when we have the real label and we have our vector of predictions, let's write it like this, looks as follows. We need to let it be the vector as well, sum by I. We need to multiply the logarithmic probability of our predictions by the indicator that this is the true class. So some of you may probably find this formula hard to remember, hard to understand, but in fact, what it is just to compute the cross entropy. For an example, we need to take the probability of the true class, logarithm it, and minus to have it larger than 0, since the logarithm of a number between 0 and 1 will be below 0. So in fact, this is just minus log true class. So that's it, nothing right. For log loss formula, it can be generalized like the same way, but sometimes you can find the following formula. You also should not be scared of this. When we have our prediction and the true class, it looks like minus logarithm probability is equal to 0 multiplied by 1 minus y. So if we like deem that y is either 0 or 1, because in some sources you may find that y is either minus 1 or 1. No, for our course we'll deem that for binary classification we have either 0 or 1. That's the formula. So if we have the positive class, indeed we need to take the logarithm of the probability of belonging to the positive class. If the true class is negative, we need to take the probability of belonging to the negative class. Again, nothing frightening is in this formula. Okay, so here if you will need to revise, you can find some examples of cross entropy, how it is applied, blah blah blah. There are indeed a lot of functions for classification, for different types of classification, but according to my practice, in 95 or probably even more % of cases, cross entropy is a solution, or some modifications of cross entropy, like focal loss. We'll speak about them later in the course, and so on. So now let's move on to the gradient descent and recall its base idea. So we have some optimization problem. We have some loss which depends on the parameters, and we need to minimize this loss by changing these parameters. So it looks as follows. We initialize our parameters with some initial values. We calculate the gradient vector of the loss based on our parameters. And what's the idea? The derivative of a function, it shows the direction of the hardest increase of the function. So if we move to the direction of the gradient, we will move to the direction of where the function increases. But since the loss function is the one which we need to minimize, we certainly need to move to the direction where it decreases the most. So instead of adding the gradient of the parameters, we add the anti-gradient of the parameters, multiplied by some value in order not to move far away from the real bottom of our function. So initialize, calculate the gradient, make the step, and repeat these two steps until the convergence, or until the number of epochs is exceeded, or until the quality, the performance of the model on some development or validation step, validation set starts plotting. Okay, so probably one of the ways of stopping this very algorithm, and it looks as follows. We start in some point far away from our local minima, and we move to the direction where the function decreases. But gradient descent incorporates a lot of heuristics, and you can see only some of them here. How to initialize the weights, should we use all zeros, all ones, or we need to use some distributions. How to select the step size. In some applications, it becomes really crucial that when you make a mistake in the order, you use 0.1, and while you had to use 0.01, you use this very value, and your functions do not converge. You have some awful results just because you selected a wrong step size. When to stop, and how to approximate the gradient. There are a lot of modifications. Again, momentum, Nesterov momentum. I hope we'll speak about them today. So let's recall the gradient descent for mean squared error, and see this example together to recall and understand how the gradient descent works. So we have our loss, right? What we need to do, we need to calculate the derivative of the loss with respect to our parameters. So I hope there is no necessity to derive this formula together on the desk. We'll see the derivation of this formula on the seminar if some of you forget about this, but I hope you all remember this, how to differentiate the functions. So the difference between the gradient descent and the analytical solution for MSE is as follows. Gradient descent is easy to implement. It can be applied even if our function is not symmetric. For instance, real cases when you need to predict the amount of some items that the shop has to buy, make it a food selling shop. When you underpredict and the shop does not get the maximum possible revenue, you lose about, I don't know, let it be 100 rubles for each item. And when you overpredict and some items, they're just like not sold by the shop and they are thrown away, you lose only like 10 rubles. So for this case, the loss function is very asymmetric. It's much better to overpredict than underpredict in this case. In gradient descent, it's easy to apply to such a loss function, and for analytical solution, we'll have a lot of difficulties. And certainly it requires less memory and computations. So any questions on the gradient descent? Should I remind some notions? No? Okay, everyone understands? Even you? Nothing personal. Okay, so let's speak about the generalization of the model. Consider that our model has an accuracy of 80% on training set, but what does it mean? How will it perform on the new data? Can we trust this model? Can we apply this? Can we use it for real world data? Of course, there are cases of both underfitting and overfitting, and it is not like using only the trained sample. It's almost impossible to detect these cases. So this is the case of underfitting. This is the true function. This is our model. Well, of course, it tries to approximate, but we can see that it does not succeed in this. This is the case of, well, ideally representing the true function, but can also be the case of okay, so let it be a good case. And as for overfitting, mostly it looks as follows. So what is overfitting? I guess all of you remember, I will not ask you. So overfitting is a case when a model has a decent quality on the training set, but fails to perform well on some development or test data. And it's caused by the fact that the model does not generalize. It simply remembers the train points and remembers which value it needs to output in these certain points, like here. So it remembers this point, but between them, this is something awkward. So that's the case of overfitting. It simply incorporates target into parameters, and we cannot trust such a model. How to deal with it? So the first and easiest way is to use some fold-out validation, development, name it how you want, set. So we have some training set we train, and after each epoch or after some certain amount of iterations, we assess our model on this holdout set. And when we see that the quality of the model on this holdout set does not increase, when it stops increasing or it even decreases, we break our training process. So it can like help us with dealing with overfitting. I hope you all know the cross-validation techniques. When like instead of using a certain holdout set, we train K models, each time selecting fold K for validation and all the other sets for training. But in fact, cross-validation is not used so often in real projects because, again, it requires the usage of K models for inference. So I hope you remember that when we use cross-validation, we cannot like average the parameters of these models or sometimes aggregate them. We need to make an inference through each of the model, and only after that we need to average the predictions. And of course, when like our task is to make a prediction quickly without delays for the user, we cannot use this very technique. But sometimes, of course, when we have like our goal is to make predictions regardless of the time, we can use the cross-validation. It can lead to some better results. But the techniques which probably like are more suited for dealing with regularization, that's the weight penalty. It was found out that when we have an overfit models, again, to like, since we find these very gaps, Some parameters will be extremely high or low. Like here is an example how the good model weights look like and how the overfitted model weights look like. The idea is to penalize the model for high weights, since in most cases high weights lead to or can signal about overfitting. But here is a very important point. Before applying regularization, it's crucial to scale your features, because if the features are unscaled and some features have a great order, like I don't know, they are measured in thousands and so on, and some other features have very small order, like they are counted in units, they'll have different orders of weights. One will have thousands, another will have units, and the regularization can just break the model performance. So an important thing, which I don't know whether you were told previously or not, when we use the weights penalty, it's crucial to use the to scale the features. So the two conventional way of applying penalties is to use either L2 or L1 regularization. L2 is applying the squared norm of our the sum of squared norms of our weights. Yeah, and L1 regularization is means applying the modules of our weights. Yeah, so that the L2 solution looks like this, and our weights will I don't know again whether you were told or not. In L2 case, our weights will not be zeroed, so they will have values close to zero, even if they are linear dependent, but they will be exactly zero in like very rare cases. And for L1 penalties, again, because the analytical solution for 2D case looks as follows, they will be zeroed, so that's it. There is another important thing which we'll speak about later in more details, but for now, let's remember this. That's the weight decay. That's the way of regularization for neural networks. And some of you may find it, or some of you who already heard about this, may find it similar to L2 regularization. And indeed, for classical stochastic gradient descent, the weight decay coincides with L2 regularization. But for some advanced methods of gradient descent, like Adam, like momentum, and so on, they are different. And a bit later, we'll see how they differ from each other. Some other regularization techniques: dimensionality reduction for features, data augmentation, wait to seminars. We'll speak about this dropout. Again, this is a special layer for neural networks. Early stopping, we've already spoken about this in the beginning. So stop training our model when we see that the quality on the development, on the validation set, do not increase. Or like another great solution, collect more data, but in a lot of cases, this is just impossible. So here are some important points about overfitting. And okay, we've spoken about the gradient descent. Let's very quickly recollect the stochastic gradient descent. It uses one or several observations to calculate the gradient, since calculating the gradient for the whole sample is very often, again, impossible in terms of complexity and memory. So the most popular extension, it's not probably extension, that's the type of gradient descent, is mini batch gradient descent. When we select k instances for the batch, we use this batch to like make the gradient step, and on each step we change our batch. Okay, so now probably the most interesting part of the lecture, that's the multi-layer perceptron. Multi-layer perceptron is called a neural network. So about linear models we have already spoken, but how to deal with some non-linear dependencies. So here is a nice example. We have two images of the cat and the rocket, but if we look like, if we look better, we can see that their shapes almost coincide. It's like a pyramid here, and frankly speaking, it's about pyramid here. And how to deal with these nonlinear dependencies, that like a linear model can simply say that they are of the same class since their shapes are equal, but it will not incorporate the values of the pixels and so on. What do we need? For extremely nonlinear dependencies, and sometimes for not extremely, for simple nonlinear dependencies, we need to do the following thing. We need to have a deep or a shallow feature extractor, which would extract the features from our object. Yeah, and then we'll have the classifier, like the same as logistic regression, for instance, which would make the prediction. But how to make this, how to build this feature extractor? Of course, we can use some pre-trained models as feature extractors. There are a lot of algorithms. Use a pre-trained feature extractor and then simply train your classifier. But the problem is that the classifier will be trained apart from the feature extractor. And if there are some important aspects of the objects which both of them need to incorporate and need to like stay in touch with each other during training, we'll miss these cases just because they are trained differently. Some cases where this is how we can deal with like this feature extraction step without using neural networks. We can like, if we have such kind of data, we can move to polar coordinates and they will be separated exactly. Yeah, and okay, we'll not have any more examples, but the problem is that more often we have some much more difficult dependencies, and again, like images, like textual data, where applying such simple transformations will not help. So can this part be done automatically and trained together to make the like best prediction as possible? I need to have this, find this very one slide. Okay, so what's the idea? The idea is as follows. For some very simple classifiers, for some very simple models, how can we substitute this feature extractor step? When we have our input data, we can have some linear model, like a simple linear transformation, and then we can apply nonlinearity. And here we can use absolutely like any function. The only requirement is that the function needs to be differentiable. But I hope you know a lot of differentiable nonlinear function. Again, if now, let's recall sigmoid. It's nonlinear, and we can find its derivative. And after this step, like we make the linear transformation, we apply nonlinearity, and that's all. We can apply some algorithms which would make the prediction. So our model will incorporate the non-linearity and will be trained as a whole instead of training some parts of it like apart from each other. So just a few nonlinear functions for you to know which ones I applied more or less. In neural networks, this nonlinear function applied after linear transformation is called the activation function. Some of the most popular activation functions are as follows. These are the sigmoid, which we spoke about, and it lies from 0 to 1. The next is hyperbolic tangent. It looks, we don't have the formula, but okay. In the modern neural networks, which appeared like 2, 3, or like 5 years ago, hyperbolic tangent is used extremely rarely, but nevertheless, like from the theoretical point of view, we need to speak about this. So the hyperbolic tangent, it's like similar to the sigmoid, except for the fact that it's limited by the values -1 and 1. So you can also have the values below 0. And two easier functions, soft plus this is the formula for it, but as an activation function, it's used extremely rarely. And the most interesting function, which by the way, its idea contradicts to what I said a couple of minutes ago. The Relu function looks as follows. So when the value is larger than 0, we have a simple function x is equal to y. So the same value as the argument. But when the value is below 0, it is substituted with 0. So when the argument is below 0, we have 0, and after this, we have this function y equal to x. The problem is that you probably guess that here is the formula, and this function is not differentiable. So in the point 0, there is no gradient weight. Luckily, the modern frameworks allow us to use this. And by the way, what we can do, we can actually derive the gradient as a rule. If the value is below 0, we apply 1. Otherwise, we apply the following value, and that's okay. So of course, sometimes it becomes a bottleneck that in 0 there is no gradient. But it was turned out that due to its simplicity, because this operation is extremely computationally cheap for the computer, and these operations, they are not so cheap because we have to exponentiate some values, and when this is a vector or even a matrix, right, it becomes computationally expensive. There are some where is it? Okay. There are some extensions of Relu. They look as follows. I will move the screen again here. So some researchers found that, not found, but they said that, okay, Relu is not differentiable, and moreover, it substitutes with 0 all the values below 0, so that calculating the gradient of the value, for the value which is 0, after applying Relu, when we calculate the gradient with respect to this Relu function, we'll have 0 value. So we can have this bottleneck when some values are 0 and they simply cannot change because of this very gradient. So some solutions were proposed. One of the most popular one was leaky Relu. It looks as follows. Again, it's not differentiable, but at least it does not have this 0 value bottleneck. So the formula is as follows. We have 0.1, for instance. This is the coefficient which can be tuned x if x less than 0, and we have x otherwise. A simple solution for this, but interestingly, in the modern neural networks, it was not incorporated because the experiments with Relu led to high results. And just another one interesting function, it is called Relu, leaky Relu, and another function called Relu. It looks as follows, and by the way, it is differentiable if memory serves me right. Relu looks as x multiplied by the function of the normal distribution. So x multiplied by the probability that the standard normal distributed, the point sample from the standard normal distribution will have the value less than x. This is the function, and for some modern cases, it's applied because due to some advances in computations, it becomes easy for the computer to compute these very fast. Okay, so let's move on a bit. No, let's go back a bit. Okay, so here is what we have. We have our linear model, some nonlinear transformation, and logistic regression. And let's imagine what's the purpose of this very nonlinear function? If our data does not have the same view as this very nonlinear function? Can we simply remove this? Will our model become more expressive than a simple logistic regression? How do you think?
No,
Why?
because if we use two linear transformation, that's equivalent to just one.
Yeah, thank you, exactly. So the combination of linear transformations is simply a linear transformation. So if we stack a lot of layers without applying nonlinearities, it will not differ from a simple logistic regression solution. So the second important point of nonlinear function lies in the fact we can incorporate a lot of more parameters, like we can stack not only one, but we can stack like 10 layers of linear transformation followed by nonlinear transformation. And we'll have a lot of more parameters, we'll have a lot of, we can like model very hard functions. Yeah, and an interesting point is that it was proved that when we have enough amount of Relu transformations, like followed by the linear layers, we can approximate absolutely any function, regardless of its difficulty. So stacking layers with Relu transformation, when we manage to deal with like overfitting, we can have absolutely, like we can model absolutely any dependency. That's it. So some terminology. The linear transformation in neural networks is called the dense layer. So the dense layer has the following formula, like we multiply our input by some matrix, and usually we also add some bias. The nonlinearity layer, or it is more often called an activation function. Some other difficult layers, not difficult, okay, advanced layers like dropout or batch norm, we'll speak about them next class. And the output layer, it's either a simple, again, linear transformations for regression task, or this is a linear transformation followed by the function softmax or sigmoid in case of classification tasks. That's it. So what are the potential caveats? Of course, since we incorporate a lot of parameters, it can easily overfit. It can easily remember just the input data and have good predictions only in these points. The problem is that very often in a neural networks, there are much more parameters than there are observations in our data set. And we need sometimes to deal with this. There are no gold standard architectures, so we need to experiment, we need to try, we need to touch this, and it also sometimes becomes computationally heavy, but like here is a very easy solution. I guess you know about the so-called GPUs, the graphical processor units, which allow to parallelize very hard computations and accelerate up to 100 to even 1000 times the computations. So if you have an access to them, there is no problems with your computations. Okay. Yeah, I look at the time. Probably this will be the last topic which we'll cover, but this is the most important one: how to train a neural network. So we already saw how to train a linear regression using gradient descent, right? For like models like logistic regression, we can use absolutely the same idea, except for the fact that we also need to calculate the gradient with respect to sigmoid function first. So let's again move to the desk. Yes, writing it down will be easier to understand. So when we have a logistic regression, we have our like features matrix X, and the prediction is made the following way. This is the prediction. It outputs a vector of probabilities, which is of shape the same as our input data. Let us have n observations and k features. Yeah, that's it. So how to calculate how to use the gradient descent for training the logistic regression. We first measure some loss depending on the target value and the output probabilities. They are of the equal shape and multiplied by 1, both of them, right? What we do next, we calculate the gradient of the loss with respect to our parameters, to V and B. Let me see. Okay, this will be better. So to calculate the gradients, we need the following thing, and the same with biases, everything the same. But how to calculate this? We can apply this great notion of math called the chain rule. That's the finding the derivative of a complex function. As for chain rule, is there anyone who does not remember? Please raise your hands. It's okay. Okay, so when we have some complex functions like j from f from x, and we need to calculate the gradient of the function with respect to its initial argument, we can do the following thing. We can first find the gradient with respect to the so-called intermediate function, right? And then multiply it by the gradient of the intermediate function with respect to our argument. So we can split this process of finding the derivative into finding several derivatives and then multiplying them. So as for our case, for our logistic regression, what we need to do, we need to calculate this very loss, and we can apply this very chain rule to help us. So first, we'll calculate the gradient with respect to the output, to this very value, and then we'll multiply it by the derivative of this value with respect to our parameters. Again, here it will probably be hard to compute this straight away since we have another function here. So we can split this into 3 multiplications. This is the first, this is the second, and this is the third. Set by B. That's it. That I named this part. So gradient of our loss with respect to our output. So for binary classification, that's the derivative of the log loss with respect to our predictions. I don't think that it's important to derive it here. Some of you maybe know that this looks like this. Some of you may probably not know this. You'll have to derive this in your first homework, by the way. Here we need to calculate the. Oh, I'm sorry, I made an error. Of course, it should look like this, because P with hat is exactly sigmoid of Z. So we calculate the gradient of this sigmoid function with respect to the argument. And the last one, we calculate the gradient of this with respect to our weight parameters. Well, this is probably easy for all of you. This is just the X transposed. Yeah, so here, this will be the derivative of the sigmoid. That's the minus sigmoid. I don't think it's easy to derive, but you also have this in your homework on your desk. So that's it. That's how we would apply the chain rule for training the logistic regression. And as for the neural networks, the idea is extremely simple. Okay, so here what we had one linear transformation followed by the sigmoid function. But what hinders us from stacking these layers and applying absolutely the same logic? So after doing this, we make the following thing. We again multiply this by some other parameters, let them be u. Yeah, so I will remove this. So this is the output. We again multiply it by some parameters, add some biases, and we apply again some other function, depending on the task, sigmoid, I don't know, or probably some other activation functions, right? We can do this, and we can stack a lot of layers, and using this very chain rule, it is extremely easy for us, even analytically, to derive the derivative of the loss with respect to some very initial parameters. So what we need to remember, we only need to remember the derivative which we have on each step of gradient descent, so that instead of calculating this separately for each component, we'll simply stack them, right, and have some predefined values. So that's it. The chain rule, guys, on the bottom. A bit more attention, just 10 minutes and I'll leave you. So to make the chain rule for neural networks, we can just stack these very things. We can use these solutions. And of course, if we can do this manually, some computers, some program can do it much faster and with probably better precision without some errors, right? So that's an easy to calculate task for the computer, since we know the analytical solution. So that's it. That's how to train the neural networks. We just apply the chain rule on each gradient descent step. So we make a forward pass. We calculate the gradient. The forward pass, by the way, again, I probably need to repeat. The forward pass is how we get this output value for the input. That's it, the forward pass of our model. Then we need to calculate the gradient of the loss with respect to each parameters. That's called the backward pass. Yeah, so we go backward in our network. And then we need to make a gradient descent step, one step, and we need to make like k steps, like either this predefined value or until the convergence, or until we see that the quality on the validation step do not change, and so on. So if you probably will inspect this PDF file, there is also a differentiation recap for those of you who do not remember how to differentiate a function with respect to the vectors, because the derivatives with respect to one values here you learn it at school, but for some values it may probably be not apparent for some of you. Okay, so that's the back propagation, and I don't think that we'll have much time yet to speak about. Okay, so the gradient descent extensions will incorporate on the next class, and for now, just a bit more minutes. Let's see the example of gradients of their calculation for the simplest neural network error, which is just exactly the linear regression trained with gradient descent. It's arguable whether this can be called a neural network or not, since it's just a linear model, but nevertheless, if we want to calculate the gradient here, so we have our input, we make our linear transformation, we have our squared error loss, right? What we do, we need to calculate the gradient with respect to our parameters. That is to calculate the gradient with respect to the output h multiplied by the derivative of the output with respect to our parameter, the same way as we did here. So, okay, as for example, we'll skip it, we'll have it on our seminar. And if we go deeper, yeah, as already said, we can just stack a lot of layers, and chain rule can easily derive the gradient with respect to all of them. So some important notions that we do not need to compute this by hands. The computer knows this mathematical rule of taking the derivative, and it can do it for us. And there are a lot of frameworks. During our course, we'll mainly focus on PyTorch framework, but if there are some of you who are like in love with Keras TensorFlow, for my group that's okay. For other groups, I do not know whether the seminarists know this or not. The last moment, just the last thing, a small recap of the lecture summary. For this, we have not spoken, okay? For the neural networks, they can approximate absolutely any functions. If we use the appropriate activation functions like Relu, they can approximate any dependency. Trained via big propagation, but they can easily overfit. That's very important thing which we need to always keep in mind. And for some nonlinear functions, we have the Relu, which is used in about 80% of cases and its modifications like Relu, Elu, etc., sigmoid and hyperbolic tangents. For the optimization, we'll speak on our next lecture and now the seminars. Okay, that's it. Thank you.